So this is a project that is funded by the European Commission. And this first slide tries to illustrate the context where this project is. So it gives an idea about the evolution of telecommunication networks. Yeah, like the very big first transformation where we have digitalized the networks until today. So this is like where we are today, where we are using IP networks and IP protocols, and for the service architecture or for the service delivery, we are using IP multimedia subsystem infrastructures and also cloud-based platforms. And so we are aware of all the limitations that we have today by using these technologies, mainly IMS. And we see that we are not competitive enough if we can compare ourselves with web players, web over-the-top players like Google or Facebook. And so the idea is to look on what are they doing and take advantage and try to leverage more up-to-date technologies, mainly web technologies. So we believe web technologies are very much the way to go, since they are ubiquitous, so you can find web engines on any kind of device. And at the same time, we also see emerging paradigms like microservices and edge computing. On the other side, you can also see that if you compare telcos with other players, that we have some limitations. For example, we are limited in terms of the license that we have to operate on geographies that are limited. Well, they are not. On the other side, you can also see that usually they don't care very much about interoperability, and for that they use walled garden models. This means that if you want to communicate with someone else, you have to make sure that you have an account on the same domain. So you can see in this slide the partners of the project. I won't go all through them. You can find in the website more information. And this is the statement about the objectives of the project. So in summary, we are trying to design and to prove with the reference implementation, that is, by the way, open source, a new service delivery framework that is not limited to telecom operators. So we want that this service framework that to be used by anyone, including the web players themselves, if they want. As I said, so this is web-centric, so we use as much as possible web technologies, and also edge computing. So this means that we also try to have peer-to-peer as much as possible for the communications. And also very important for us is security and trust. So from the very beginning, we have designed the architecture having in mind all the requirements in terms of security and trust. And then we have this service concept that we call Hyperties or hyperlinked entities that were conceived to be agnostic of the service type. And so in our use cases, we are trying to demonstrate that they can be used for different types of services, including the usually traditional telephony-based services like human-to-human voice communications, but also more advanced and enriched communications like contextual and social communications, and also machine-to-machine and Internet of related services. Content-oriented service at this point are not, we don't have any scenario where this is demonstrated, but conceptually this should be also possible. So having this in mind, these are the main principles that we have considered. So we are applying microservices architecture paradigms and patterns, edge computing paradigms, and at the end, the vision is to have a global network of interconnected services that we call Hyperty, that are executed as much as possible at the edge, including on the end user device. And so a few words about the Hyperty concept. So the Hyperty concept is based on the microservice pattern. So this means, in general, that is autonomous business. It implements a business or a set of business capabilities in with having not having as dependencies. So the idea is to have it independent as much as possible. And we can say that they are similar to user agents or bots in the sense that they perform tasks on the behalf of a user. And the user here can be not just a human being, so it could be also a device, a physical device or a physical space. And it is associated to an identity. And this identity is decoupled from the stakeholder that is providing the service logic, so the Hyperty itself. So the idea is to give the power to the user to select the identity to be associated to this Hyperty. So, and for this, it means that we allow to have certain external IDPs, identity providers, to be used in the service delivery. At this point, Hyperties are implemented in JavaScript, but in future we could see that other languages can also be used. But that's what we are doing today, since we are using as much as possible web technologies. And so this figure tries to illustrate the concept. So at one level, we have the user plane, where we have the different users. In this example, we just have like human being users, but it could be also a physical device. And then we have the Hyperties that are associated to this user, that are running on top of some web technologies like a browser or Node.js. And so the relationship between users then can have a direct map with the communication between Hyperties. And we will see later how these communications are handled. And then this is the main picture for the architecture. So this gives a high-level view about the functional architecture. So we have here the runtime where Hyperties are executed. In this case, this is a device runtime. But we can also have a server runtime. So Hyperties can be executed on both server-side or device-side runtime. And then Hyperties or that are being executed in one runtime communicate with other Hypertys through the message node. So the communication is message-oriented communication. Then we have the catalog. So the catalog is a function that provides descriptors and also the source codes that can be deployed in the runtime. And then we have the registry. So the registry is a place where, as soon as the Hyperty is instantiated in the runtime, information about this instance is registered in the registry. So this means that then the Hyperty instances can be discovered by other Hypertys in order to communicate with it. And then we have the IDP. So as mentioned earlier, Hypertys are associated to identities that can be handled by external IDP. So this means that the service provider that is providing the Hyperty can be different from the identity provider. And in this way, the user can select the identity that it prefers or it trusts more, the IDP it trusts more. Yeah, so this is just to give you an idea about the main functionalities that are required. From the developer point of view, you are not supposed to know these details. So this is like functions that are provided at the backend, and you don't have to care about it. So the idea is that the framework provides some local APIs that abstracts from all these functionalities that are being provided at the backend. So a few words about then the communication through messages. So we have a message-oriented framework where we have different functional routers. So please don't think this is like an IP router. This is like a functional router that routes messages through the Hyperty. So one Hyperty can send a message, and then the different routers can route the messages according to some rules until it reaches the target Hyperty. And then we have routing management functionalities that can set these rules, and at the end to set the route path in order to ensure messages are delivered to the right Hyperty. And these rules can be programmed. So according to the APIs that are provided to the developer, the messaging framework will define and set the rules, the routing rules in the routing management functionality. Again, from the developer point of view, you don't have to care about this. So this is also abstracted from the API. So this is just to give an idea about the functionalities that are provided at the backend. Then one of the big challenges that we have is to provide interoperability without having the need to standardize protocols. And for that we use a concept that we call protocol on the fly, which is a very simple concept that takes advantage of the possibility to select and download scripting languages like JavaScript into a runtime. And so this means that during design time you don't have to be limited to a certain protocol stack. That protocol stack can be selected and dynamically deployed in the runtime in order to ensure that the different endpoints can communicate each other, so that they are using the same protocol stack. So this means that in the same runtime you can have different protocol stacks deployed, and according to the remote, the protocol stack that is used by the remote runtime, you can select the one that ensures this interoperability. So in this case, if you want to communicate with an Hyperty that is on this runtime side, you'd use protocol stack P1 that lets you communicate through message node 1 with the remote runtime. And this protocol stack can be dynamically loaded into the runtime from the catalog. So again, this is something that will happen behind the scenes for the developer perspective. Just to give you an idea that this mechanism will let Hyperties interoperate each other independently of the protocol stacks that are used by the different domains. And for that, then we can achieve interoperability without having to standardize protocols. Also, a few words about the trust model. So, according to some policies, so the runtime also features a policy engine that can be used to decide whether a certain message that is sent to an Hyperty requires or not to have some assertion that the remote Hyperty can then use to validate that, for example, the identity that is associated to the Hyperty is really the one that claims to be. And so this generation of assertions and validation of assertions is provided by an external IDP that can be selected by the user. So this means that also there is the possibility to have a trustful relationship between the different Hyperties, even if they are delivered from different domains, and that this trust can be provided by external IDPs that are selected by the user. Again, this is provided behind the scenes, so the developer don't have to care about it. But the API then provides the required functions to see whether the message is providing information that is trustful or not. Then, so we are just reaching the end of the more theoretical presentation, and the last concept is the reporter and observer communication pattern. That is also a key concept in order to allow interoperability in terms of the semantics of the information that is exchanged between the Hyperties. And for that, we use data synchronization. So there is a data object that is a JSON data object that is used by an Hyperty that we called the reporter. That is the only instance that has permissions to write on these data objects. And then all the changes that are made on these data objects are propagated to all the Hyperty observers. So these are the Hyperties that are only able to read these data objects. They don't have permissions to write on it. And so this is the way how Hyperties communicate, through data communication, through synchronization. And this data is a JSON data object. So the APIs that developers will use is based on this paradigm, communication paradigm. We will see in a second how this API looks like. But for the developer perspective, this is very important to understand. That communication is done through data synchronization. And the format of this data object is formally described with a JSON schema in order to ensure that two different Hyperties can communicate each other. We have to ensure that both can understand this schema, the JSON schema. So this is a simple way to formally describe a JSON object. And in this case, this is an example for the hello data object that you'll see in a moment. So basically, it has a constant hello that is of type string. So this is the scheme of the data object. We'll see also in a moment what is the scheme in this case. And the attribute hello is of type string. So we have two attributes here. Then some examples of data objects that we are using in our demonstrations are provided in this slide. So this one is for the connection. The connection data object is used to support WebRTC communications. And this means that the data format is aligned with the standard WebRTC API. So basically, in the different, so we have two objects. The connection is the one that is created by the Hyperty that initiates the connection or the call. And then it has information about the peer connection associated to this endpoint. Then we have the remote peer that receives the request for the connection. And for this remote peer, it will handle another data object. It is the peer object. And the peer object then also have all the information that the WebRTC API provides. So this means that in terms of interoperability, you just have to ensure that your Hyperties are using this schema that is basically aligned with the WebRTC API to allow interoperability between all the Hyperties that are used. And then the data objects are identified through URLs. And the scheme of the URL will depend on the data model. So in this case, a connection data object will use this connection scheme, and then the domain of the service provider of the Hyperty is here, and the rest is information about the communication instance. So in this case, the connection object. So this is the way to identify a certain connection instance, in this case a WebRTC connection, through your URL. Another example is the context type Hyperty that can be used for Internet of Things and machine-to-machine use cases. And in this case, the scheme is context, and then the syntax is the same. So you have the domain, and then the identification of the object. And for this type of object, we also have a JSON schema that can be used to ensure interoperability between Hypertys that are compliant with this JSON schema. And in this, here you have an example of a JSON object that is compliant with this JSON schema. In this case, it provides two types of context values from a bracelet. So in this case, it is collecting information about the steps of the user that is wearing the bracelet, and also about the level of the battery. And finally, the communication model can be used to support different types of communications. In this case, we are using for chat messages. And so we have the communication object that is reported by the Hyperty that has created this chat. And then we have a collection of the messages that are sent by all the peers that are involved in this chat communication. So in this case, we are using a children chat message collection that is used by all peers to send these messages. So we also will see with the example of the group chat how this can be used with the framework API. Then just a few words about the descriptors. So as I said, Hypertys are described, formally described, in order to give information about the capabilities of the Hyperty. And what is important to define in the descriptor is mainly the supported data schemas. So the data schema itself is also hosted by the catalog, and then the types of resources that the Hyperty supports. So we have an enumeration that defines the different types of resources, and in this case, this Hyperty is supporting chat resource. So this is the information that is defined to describe each Hyperty.